Welcome to Latency SLOs Done Right. I'm your host, Fred Moyer. I'm a developer evangelist at Circonus. That's my Twitter handle with a PH instead of an F. A little bit more on me later. But first, I want to ask folks, is latency important to you? You know, this is an SRE conference, so I assume it's important to a lot of people here. Anyone? Pretty much everybody. That's what I thought. So I'm going to ask you a question. You know, for any of your services within the last month, you know, can you answer how many of your requests were served within 500 milliseconds of, you know, served under 500 milliseconds? That's kind of a specific question, and, you know, 500 milliseconds might not be your SLO, but does anyone have an idea if they met that, or so some people? Okay. How about, you know, if I asked you how many requests were served under 250 milliseconds? So some folks, all right. This is good. This is encouraging. But I ask you, like, how would you answer that question for your services? What tools do you have available in your systems? I'm sure everyone here is using some sort of monitoring tool that will tell them, like, hey, you know, here's a request breakdown of how long, you know, it took to, you know, serve certain endpoints. And I'm sure everyone, you know, is aware of that to a certain degree. But I'll ask you, like, you know, how accurate would your answer be for those services? What kind of error bars do you have? You know, if you say, like, hey, I had, you know, 50% of my requests served, you know, under 2 seconds, you know, is that 50% of those requests, you know, say if that's 1,000 requests, is that plus or minus 200 requests? You know, have you looked at the accuracy of your monitoring system and how that's actually generating those numbers? So we're going to talk about that today. I'm Fred, and I like service level objectives. You know, I work at Circonus as a developer evangelist, which means I'm an engineer who talks to people. I've been writing code and breaking production services for about 20 years. I've had some interesting incidents. I worked for Symantec several years ago, actually about 10 years ago, and they had message IDs that were 32 bits, and I got a call one New Year's Eve when it ran over 4 billion number of messages. That was fun. I like C, I like Go, Perl, and Postgres. So let's dive right in. This is our talk agenda. Going to go over SLOs really quickly. I'm sure most folks here are familiar with those. We'll talk about a common mistake people make when computing those. And then we'll go into 3 different methods for computing SLOs, with log data, by counting requests, and with histograms. So most folks here have probably read this book, Site Reliability Engineering by Google. You know, it established these 3 terms, you know, SLIs, service level indicators, SLOs, service level objectives, and SLAs. You know, that term has actually been around quite a while, as everyone is probably familiar with. There's been 2 recent books that have come out which have expanded on this. Seeking SRE is one. There's a chapter in there by Theo Schlossnagel, the guy who got me into all this SLO stuff. And there's also the Site Reliability Workbook. Chapter 2 in there discusses computing SLOs exclusively. And I'll draw on some of that material in the next few slides. But there's also a great video here by Liz Fong-Jones and Seth Fargo. I've got the YouTube link there. The video is called SLIs, SLOs, SLAs, oh my. And it talks about how SLIs drive SLOs, which inform SLAs. So as an example, I could have a service level indicator of, you know, that says 99 percentile latency of home page requests over the past 5 minutes must be less than 300 milliseconds. I'm sure everyone here has, you know, a monitoring system that they can use to, you know, capture that kind of data. You know, 5 minutes is a fairly common interval. You know, most monitoring systems out there, both open source and commercial, roll up to that by default. And, you know, you can get your 99th percentile from, you know, a number of different means. So that's an SLI. So SLOs. With that SLI, my SLO could say my 99th percentile homepage SLI will succeed 99.9% over the trailing year. So what that means is, you know, if I chop up my trailing year into 1,000 pieces, my SLI is going to succeed for 999 of those pieces. And this is, you know, SLOs are internal targets. There's been several talks here at this conference on those. It's mentioned in those books, so I expect, how many people here are familiar with SLOs? How many use them? Actually, wow, it's good stuff. But these are internal targets. And then we have SLAs. These are crafted by lawyers, and this is basically a more conservative way of expressing, how you think your service is going to perform. Does anyone here have SLAs but not SLOs? A couple of people? Well, I got news for you. You have SLOs, and those are your SLAs. Don't tell your lawyers, because they're not going to be happy about that. Because that means that the internal objectives that you are working towards are also those conservative objectives that, when contracts are made for, your company to deliver services, your lawyers have said, like, let's put that SLA bar really high, because if we violate that, we've got to give the customer a cake or something like that. Typically you just have to give them back more money. But so you really want to, this is where SLOs protect you and protect you from other parts of the organization. So pretty quick refresher on SLOs. So let's jump into a common mistake made when computing SLOs. And that is averaging percentiles. How many folks here have averaged percentiles? Oh, am I the only one? Okay, I've done that. But what that basically says is, what this math equation here says, if I take, if I've got a set of data that has a P95 W1 and another set, and I've got a P95 for that data set, if I try to average those together, that is not equal to the P95 if I take both sets of data and combine those together and then calculate the P95. This is a very common mistake. You'll see it on blog posts a lot, people doing this. And the reason that it's fairly common is that when everything is working, all your nodes have symmetric workloads and everything's behaving just fine, this approach works. You get pretty much the right answer. But where this starts to fall apart is when your workloads become asymmetric. If you've got a couple nodes that go down, or a couple nodes that are really slow, one node that's really slow and servicing a lot of requests, that's when this will bite you. So here's a graph of P95, P99 at the top, P90, and median request latency times. On the left axis, on the y-axis, the first bar is about 200 microseconds. And so here, you probably have generated something like this, so this should be pretty common. You can see that, for most of this, we're getting response times around 180 microseconds, and then, we have a spike and it jumps up and, goes to about 300 microseconds. So I'll ask you, what's the P99 across this entire range? And you might look at this and you might say, well, these are all aggregates, so I can't say for sure, but I can take a guess and say, it's probably, slightly above 180 microseconds, just by, kind of doing a weighted average in my head. And that's, it's a fairly reasonable thing to do. But what if I told you that 99 of all requests happened where the spike occurs? I mean, volume is not present on this graph. And this seems fairly reasonable. Everything's humming along, and then all of a sudden you get up on Reddit or Hacker News, and bam, your service gets hit, and your service slows down. And the bulk of requests here could be right in that interval. Well, now when I ask you what your P99 is, your answer is going to be a lot different than the previous slide, because that that critical factor, volume, cannot be shown here in this graph. Here is a histogram, a distribution of latency requests for two services that I generated. We'll call it web server blue and web server red. And I plotted the P95 for blue, and I plotted the P95 for red. So let's take a look at some of those numbers. If blue is 220 milliseconds and red is 650 milliseconds, if I average those, I get 430 milliseconds. But if I combine that data together and I take the P95 of the union of it, I get 230 milliseconds. And that's a 200% difference. That's a fairly significant error. And this is just 2 nodes with largely asymmetric workloads. But this is kind of illustrates what can happen if you assume that everything just works as you assume it should, and you start taking averages. And here's kind of a graphical representation of that. This is the magnitude of the error, fairly significant. So this is something to watch out for, and it's something that you don't often see if you're taking the approach of averaging percentiles. And you might ask, well, how does that happen? Why don't people know about this? And one of the big reasons behind that is the tools that are out there make this really easy to do. You have like graphite, is a very common tool. You can plot P95s, and then you can write an expression that combines those and averages those. And graphite's not going to complain. It's just going to do what you've asked it to do. It doesn't check your math. But then you might say, well, I can use a log parser like mtail, and I can collect all those metrics. I can collect the raw latency values for my logs, and I can store those. But then I ask you, okay, what are you actually storing there? Because mtail is going to aggregate, calculate these aggregations and store those aggregations. And so again, you have a tool that's, if you just use it blindly without understanding what it's doing, can very easily lead you down this path and give you the wrong answers. And you can see those error bars are sometimes very large. So we took a quick walk through a common mistake. Let's dive in and start calculating some SLOs. Calculating SLOs with log data. This is very easy to do. Here's a pragma for configuring either an Apache or an Nginx log, where I can take the number of milliseconds that a request took, and I can extract that, and I can get that data out of the logs very easily. I don't have to go change it in my application or do anything. I just have to change the configuration file, and your log's already most likely configured to output this. So something like this, grabbing latency like this, I got about 100 bytes worth of storage for each log file, which is about a gigabyte, for every 10 million requests. Not huge, but if you're dealing with web pages, now you've got this value for each of 100 requests on a web page in some cases. So it can very easily get very large. So how do people deal with these logs? They can dump them into HDFS, run a Hadoop job on them. They can feed them into Elasticsearch or Splunk. Splunk is capable of calculating P95s across log data. I've done that myself. Or they can just use a Unix command like grep out latency out of the logs. Pick out anything that's over their SLO of 550 milliseconds, and count that up. So there's a lot of tools out there that make this really easy to do with log data. And once you have that data stored, all you need to do is extract the samples for a given time window, sort those samples by value, and then find the sample count. In the case of like a P95, that's 5% down by count from the largest value. That's your P95. It's really easy to do. And again, there's tools like Elasticsearch and Splunk that have functions built in to do this. How would you get your SLO from that? Simple. You've got all your SLIs there, so just take 1 year of samples of those, chop it up into 1,000 slices. Each slice, calculate the SLI. Did you meet your P95 SLI for 999 of those slices? So you met your SLO. That's simple to do. There are some pros of this approach. It's easy to do. It's easy to roll your own processing code. I just gave you the algorithm right here. Very simple. And it produces accurate results. But there are some dark sides of this too. It's very expensive to do. If anyone here is familiar with log analysis software pricing, it can get very expensive if you're handling terabytes of logs. You can do sampling to kind of mitigate the scale effect, but that kind of skews the accuracy. It can be slow because you're dealing with tons of data, and it's very difficult to scale. So this isn't a great approach, but it does produce accurate results. So let's take a look at a different approach, calculating SLOs by counting requests. So how would I do that? Well, I can establish an SLO threshold or an SLI threshold, and I can keep a running count I can instrument my code and say, up the count if this request took longer than my SLI. So to calculate my SLO by doing that, I can count the total number of requests, and I can take the number of failed requests, divide that by the total number, and multiply that by 100, and subtract that from 100, and that gives me my success ratio. So this is mathematically very simple to do. And you can do this with most commercial or open source monitoring systems right now. You just have to instrument in your app to fire off a counter each time you violate your SLO or you go under it. So this is a similar approach to Prometheus's less than or equal to histogram implementation. You're counting the number of requests that fall under your threshold. Very simple. Here's an example of this graphed out. The gray section is the number of total requests, and I keep a count of requests that had errors in the red section. So I can count my number of bad requests, my number of total requests, plug them into the equation, and 96.2% of my requests were above my threshold. So my SLO was met. It's a pretty simple approach. It's simple to implement, it's performant, scalable, and accurate, but there are some very crucial drawbacks to this. When you take this approach, you're working with a fixed SLO threshold. So if you say 500 milliseconds, I think that's a little too high. I want to drop that down to 400. You can't retroactively look at all of your historical data and evaluate it against that threshold. It's impossible to evaluate it over time. And also, you don't really have an idea if 500 milliseconds is the number you want, because you're pulling that out of thin air. You've got to go through a great deal of iteration with this approach to do that. So that's one of the drawbacks that makes this not a great approach. So let's hop on to histograms, which is kind of my favorite topic here. How many folks here have used histograms? Impressive. That's the largest of any time I've given this talk. So histograms are also known as distributions. Here's an example histogram. Looks like a bar chart. And on the x-axis, we have the sample value. On the y-axis, we have the number of samples. There's some descriptive statistics about this. The highest point is called the mode. You can have multiple modes in a histogram. The median is the point at which you have an equal count of samples above and below that value. The mean is different. The mean is the sum of the values divided by the number of samples. Different statistic. And then you've got percentiles, which here are expressed as quantiles. 90th percentile expressed as Q.9 is where 90% of the sample count is below that value. And your Q1 is your maximum, that's your highest value. Guillotine has an excellent website here where it talks about high density histograms. I'd encourage everyone to check that out. So there are several different histogram types. I've listed 5 here. You can have linear histograms, approximate histograms, fixed bin, cumulative, and log linear. And when I say types, these are really descriptive attributes of histograms. I can take these and combine them to create a histogram that has several of these attributes. For example, I can have a cumulative log linear histogram, which means that my bucket size, my bin sizes increase by a factor of 10, but each successive bin has the count of bins that are less than it. If folks here have used Prometheus, Prometheus uses a fixed cumulative style of histogram. And that's cumulative over space. I can have that cumulative over time also. I can have a histogram that counts, for each bin, counts up the number of samples over time. So there's a number of different approaches here. And I've got some talks where I go into this ad nauseum, really in depth. Here's the open source log linear histogram that I've worked with that we have released on GitHub at Circonus. It's a log linear histogram, and what that means is for each of these bins, the term bucket and bin are kind of interchangeable. If you look on Wikipedia, it'll call it a bin. But from 100,000 to 1 million, I've got a bin size of 10,000. And at 1 million, that bin size goes up to 100,000. And so this has some properties with it, and one of those is it's you don't have to go out and figure out what bin sizes you need. This just gives you a preset number of bins that because they're increasing by 10 every factor of 10, the statistical accuracy of the data remains the same. So here, as an example, I've shown the average at 500,000. I've shown the median at 600,000 and the 90th percentile at about 1 million. And there's about 50 million samples in this histogram. Histograms are volume invariant, which means that to store this in a memory structure, I'm storing a count for each of these bins. So that count doesn't matter, if it's 5 million or 50 million or 5. That data structure is, this histogram is going to take up the same amount of memory because it's volume invariant, and that makes it a very useful data structure for latency SLOs. Here's an example of histogram latency data in production. This is syscall latency provided by eBPF. There's about 20 million samples here. You can see that there's, for the light green series, there's 3 different modes. One to the far left, that spiky one, and then the second mode, which is a little bit higher, and then the third mode here, where you can see, the bin size is increased by a factor of 10. Histograms have a property called mergeability, which means that I can take 2 different histograms, and as long as they have the same bin boundaries, I can merge those together. And the way I do that is I just add the counts together for each of the bins that span those values. And I can not only do that for space, but I can do that for time. I can take 2 web servers that were in the same time slot and merge those together, or I could take 1 web server and merge the latency data from that over the past year. And this is an important property. This is not something that you can do with percentiles, as I mentioned earlier in my talk. So let's talk about computing SLOs with histograms. If I want to ask how many requests were faster than 330 milliseconds, and I've got a latency distribution, a histogram of request latency data that's like this, how do I do that? Well, I start at the left, the lowest value of lowest sample value, and I walk the bins from highest to lowest, and I keep summing those counts. And I stop when I hit my SLI of 330 milliseconds. So I sum the number of counts up, and I'm done. That's it. I know how many requests were under my threshold of 330 milliseconds. Very simple math to do something like that. And I gave this talk, a lightning version of it, back in, I think, October of 2018. And Liz, one of the conference organizers, caught this. And she said, well, this is good, but you got to make sure that the values that, your SLI value that you pick falls on a histogram bin boundary. So you have to understand what your binning algorithm is. So for the log linear histogram that I showed here, what's my binning algorithm? Well, for this implementation, I've got boundaries at 320, 330, 340 milliseconds. Conveniently, that lands on 330, which was my previous one. And I've also got them at 10, 11, 12, and 13. But I've also got bin boundaries, at 10 millionths, 11 millionths, and 12 millionths. Because it's log linear, these bin boundaries occur at spots that, in worst cases, my error is bounded by about 4.3%. I'll give you an example. If I've got a value of 10.99 and I shove that into a bin between 10 and 11, that gets interpolated to 10.5. So 10.99 minus 10.5 is, is close to is about 5% or close to 4.3% if you throw in a little bit of additional math. So in worst cases, you have, with one sample, in the extreme side of a bin, you have about 5% error. But in practice, when you're taking thousands of latency samples, that error drops down a lot more, gets close to 0. And this assumes you have, 2 significant digits for each of these entries. And these bins in the implementations I've shown span from 10 to the negative 128th to 10 to the 127th. So there's a decently wide range that should cover most of your latency ranges. So pros. Histograms are space efficient. In practice, a histogram that I've shown, takes up about 300 bytes. So it's about 10 times more efficient than logs. The thresholds can be chosen as needed, and you can analyze those as you want. You can apply statistical methods like interquartile ranges. Count below is a very common statistic to apply. That makes calculating SLOs very easy. You take your SLI value, say 300 milliseconds, and you apply count below, and you've calculated your SLO. They're mergeable. You can aggregate data across nodes. The implementation I showed is very fast performance-wise. The C implementation has nanosecond level insertions, microsecond level percentile calculations. As I've showed you, the math is very easy to do. It's got a half a bin error size, and there's a number of open source libraries out there. There's Guillotine's HDR histogram. There's the log linear histogram I've shown. There's some other histogram approaches out there like Ted Dunning's T-Digest, but that does have some drawbacks in terms of accuracy. Histograms do have some cons though. The math can be complicated, in terms of, it's not as straightforward as just counting the number of good requests and counting the number of bad requests. And there can be some loss of accuracy. So let's talk about how we can calculate log linear histograms with Python. So as I mentioned, if I take our open source library written in C, there's Python bindings that are bundled with that. So I can install the C library, and then I can pip install the Python bindings. And I can write some Python code that looks like this. I can create a new histogram, and I can just say insert a bunch of values here. And I can print the count, I can print the sum, and I can print, in this case, the median. So this is Python code. This is pretty easy to do. So if I've got a file of latency values from several web servers, I can easily programmatically calculate my SLI with an approach like this, and consequently my SLO. And we can also generate plots of this. And this is pretty easy. I can pull in PyPlot. I can create a new histogram, and I can programmatically suck in all that data, either from a text file or from a key value store, and I can call plot on that. And I can, this is standard Python library functions, and I can generate something like this, which is what I showed earlier in the talk. This, this code here is how I actually generated this. So that was pretty fun to do. So kind of wrapping it up, stay away from averaging percentiles. Spread the word that you can do that and the tools make that possible, but you don't want to do that. Counters or histograms are probably the two best ways to calculate SLOs correctly. You can use log files to do it, but you can run into some scaling issues there because that is quite a bit of data. Histograms tend to give you a great deal more flexibility than latency threshold, but they're only, there's a couple libraries that implement them. Guillotine's HDR histogram, and libcirc-LOHist. Both of these implement histograms as what are called sparse histograms. Full support for histograms in time series databases isn't that widespread yet. Company I work for produces IronDB, which does use histograms there. You can take that, you can take this approach with key value stores or text files or something like that. But at scale, you're going to need to kind of think about the approach, even though it is very efficient. And by scale, I mean, tens or hundreds of millions of requests. So that's it. This is me. I've got some, histogram talks on my SlideShare account that go into some gnarly depth about those details and how to calculate quantiles with interpolation. If you've got other questions, tweet me or hit me up on our Slack channel.